Okay, welcome to the set theory seminar. We are really pleased to have Joel Hamkins as our speaker today. Feels like a little bit of a reunion of CUNY people. So we're all looking really forward to his talk on realizing Frege's basic law V or five, provably in ZFC. Go ahead.
Thank you very much, and it's such a pleasure to be at CUNY and see all of you and friends from old times. So really fantastic. Thanks for coming. Feel free to ask questions in the middle if something isn't clear, and I'll try to address it. So, okay, so I'm going to talk about Frege's basic law 5, and maybe I just want to kind of set the stage. This is going to be slightly more philosophical, maybe, than the typical CUNY set theory seminar talk, but it's of course involving both, so I hope it's okay. So, okay, so in Frege's system, he's distinguishing sharply between concepts and objects in a way that I think accords with how we often think in set theory. Namely, there's a kind of realm of objects, so constituting the universe of individuals, a domain of discourse, and the quantifiers are taken to range over this realm of objects. And then Frege also is having this idea of concepts which serve in effect as predicates on the domain of objects, because a given object either falls under the predicate or doesn't. I mean, he has this sort of course of values, this sort of function way of talking about it, but basically I think it's not inaccurate to say Frege's system has this realm of objects with concepts sort of layering on top of it. And then he has this idea of the extension of a concept, which is what basic law 5 is about. And he wants to associate to every concept an object, which he calls the extension. And it's important to my way of thinking to realize that the contemporary connotation of extension is a collection. And this is not necessarily present in Frege. So the extension of a concept nowadays we think of as the set of individuals that fulfill the concept, or the class of individuals that fulfill the concept, and in particular, it's a kind of collection. But for Frege, he doesn't have that connotation necessarily. So, okay, so we want to associate, though. He wants to associate every concept an object which represents this concept, okay? And this, as I said, the extension terminology today carries this collection connotation, and please set that connotation aside, and you'll have a better understanding of what's going on with basic law 5.
Okay. Sorry, is he more specific about it? Like, in a way,
yes,
it sounds a little bit.
5 is exactly this way in which he's specific. So let me just get it, and then I think it'll answer. Okay, so the extension, it should be a conceptual invariant in the sense that it's the same for equivalent concepts. So this is expressing, I think, exactly the sense. So if concepts are what he says is extensionally equivalent, they have all the same instances, then the extension objects associated with them should be identical. Okay. And from a kind of contemporary point of view, this looks like class extensionality, because if you think of the extension of the class as the class of instances, then the class of instances of F is equal to the class of instances of G if and only if F and G have the same instances. Okay. But for Frege, this is an object, it's not a concept, it's an object that's representing the concept.
Can I make
sure,
it?
Please. Yeah.
I mean, Frege argued that arithmetic is part of logic. This was the whole point of his project. Right. And he needs this in order to do this. Now, we can give it any interpretation, but if I understood you correctly, then the interpretation that you give wouldn't satisfy Frege. I mean, this is not a way for Frege out of the contradiction. I mean, when the contradiction has been discovered, Frege devoted years to find something that would enable him to realize his project. And there were some attempts and it failed. So he gave the whole project up. So I think that you makes it part of ZFC or something like that, but that wouldn't be a solution that satisfies Frege.
That's probably true. So maybe it's important to say that really what the sort of theme of this talk is not to have a set theoretic understanding of Frege, but rather to have a Fregean understanding of set theory. This is what I'm trying to do. So I'm inspired by Frege's ideas. I'm going to prove some theorems in ZFC, and they are going to have a kind of Fregean aspect to them, which is historically interesting, I think, and it definitely affects these issues that you just mentioned about the contradiction and so on. Okay, so I want to understand, because this is his axiom, and what it's saying basically is that the assignment of every concept to an object, which he calls the extension, is an invariant with respect to this equivalence relation. So when two predicates have the same instances, then they get assigned to the same object. So it's basically something like the kind of reduction that happens in Borel equivalence relation theory. You know, we're assigning to the concepts an object in such a way that identity of those objects is the same thing as equivalence of the concepts. Okay, so now, of course, Russell is famously credited with refuting Frege's system with the Russell paradox, which I'm sure everyone here knows, right? So if every concept determines a set, right, then we can make the Russell set of all this non-self-membered sets. And if that is indeed a set, then it's a member of itself if and only if it isn't, which is the contradiction. Okay. And Russell himself pointed out the similarity to Cantor's proof that the power set of every set is bigger than a set. The logic is basically identical, right? And so therefore the Russell paradox can be seen as the assertion that in any domain of individuals, there must be more predicates on that domain than elements. It's another way of understanding what's going on, right? The power set is bigger, there's more sort of classes than there are objects in any mathematical situation. But basic law 5 is seeming exactly to contradict that, right? Because it's assigning to every concept an object. And so that's why people say Russell's argument refutes basic law 5. Okay, that's the traditional way of describing the situation. And Russell and Frege both said that. Okay, so now I want to view set theory in this Fregean light. So the cumulative universe is, of course, a domain of individual objects, the sets, and the quantifiers, the first order set quantifiers range over that domain, and we make assertions about those objects in set theory. That's what set theory is about. And we can express concepts about sets, namely, you know, being an ordinal, being transitive, being, you know, all of the various concepts that we talk about in set theory are predicates of those objects in the set theoretic realm. So being equinumerous, being the power set of y, x being the power set of y, and so on. Those are all concepts, right, expressible in the first order language of set theory about the realm of individuals. And so basically, in that way of doing set theory, which I think is completely standard, is to express a concept, I mean, to provide a concept is to express it in the language of set theory. So this is like this sort of definable classes, right? So definable classes are the concepts that we use in set theory. If we're doing ZFC, first order set theory, then these are the concepts that we have available. Okay, and I think many set theorists operate in the set theory I have described. I see Andreas is here, and so I'm going to quote him here. So he stated explicitly that proper classes are not part of the set theoretic ontology, and this is what he wrote. Proper class, I think this was on Math Overflow. I can't remember the reference, but I think it was Math Overflow. Proper classes are not objects. They do not exist. Talking about them is a convenient abbreviation for certain statements about sets. For example, V equal L abbreviates all sets are constructible. If proper classes were objects, they should be included amongst the set. So the idea is that if you wanted to treat classes as objects, then you didn't make the universe tall enough. You should have continued the cumulative hierarchy higher. Okay. And okay, so only the sets are the objects, and the classes are predicates on that realm. This is a very Fregean way of doing set theory. Kanamori also works that way. So in the higher infinite, for example, when he talks about the Kunin inconsistency, so that's the theorem that says there's no non-trivial elementary embedding J from V to V, he explicitly says it's a schema of theorems, one for each J, and the treatment of classes in the higher infinite is classes are just definable classes in set theory. And so he's taking J as a definable class, which is a very strange thing to do. Actually, I sat next to him once at a dinner at the Wooden Fest a number of years ago and told him my objection to this way of doing it, which is that, oh, I haven't written it here, but it's a peculiar theorem to take in this line because, of course, it's much, much easier to refute the existence of a non-trivial definable elementary embedding. And this is the, I think it's a folklore result, but Suzuki published the argument. You don't need the axiom of choice. It's a very straightforward argument to refute definable elementary embeddings. And the real content of the CUNY inconsistency is really in the non-definable case. That's where you need the delicate combinatorics at the level of lambda plus 1, lambda plus 2. So, okay, but anyways, that's Kanamori's line, which is also aligning with the Bloss quote. Okay, so my aim is to show that basic law 5 holds in Zermelo-Fraenkel set theory. I'm going to prove it. I'm going to define what the extension objects are, and I'm going to prove basic law 5 as a theorem scheme in ZFC, or ZF, I guess. So, so the way I'm thinking about concepts is only definable one. So this is the Kanamori way of doing it, and the Bloss way, and so on. We're going to do ZFC set theory with definable classes, and I'm going to tell you exactly what the extensions of any concept are, and we're going to prove basic law 5. Okay, I'm going to define the extensions, and I'm going to prove that it satisfies this equivalence, which is exactly the basic law 5 equivalence. Okay, so, right. And in particular, I'm going to achieve a definable solution. It's going to mean that the epsilon operator here, the var epsilon operator, is eliminable. So it's a deflationary account of basic law 5 in set theory, because you're going to be able to refer to the extension of a concept, but actually anything you say about it will be eliminable and equivalent to something in the language of set theory alone. Okay, so this is the theorem. There is an association of definable classes with objects, and it's definable in several senses. If you give me a class explicitly, so if it's intentionally given, okay, in other words, I have the formula and the parameter, then I can define the identity of the extension object by in the first order language of set theory using that same parameter C. Okay, so if you give me a class explicitly, then I have an identity criteria expressible in language of set theory with the same parameter that tells me which objects are the extension. It's something like the Julius Caesar problem for Frege, right? He wants to know, is something a number or not? So this identity is it the extension of this concept or not? That's expressible in the language of set theory for my definition. Okay, and then furthermore, there's a uniform version. If I have class functions, so I'm mapping every individual I, every set I to a class. Okay, so it's presented uniformly for some classes I. So if I have a class, possibly a proper class of sets, little I, and I define this two-dimensional thing, so I've got the sections, so I'm giving you a list of classes, then I can define the function that maps little I to the extension. Remember, the extension of a class is an object, is a set. It's not the class of all instances, it's a set that's representing that class. So then I can uniformly define the function. And then in any case, the full mapping is second order definable in my intended model here, which is equipping the sets with the definable classes only. Okay. And then such that basic law 5 is fulfilled. So these, part 1 is the definability attributes of the extension assignment, and part 2 is saying basic law 5 holds for that assignment. Okay, so that's the theorem that I'm claiming. And let's just jump right into the proof, unless there's any questions about what it is.
I have a question. In part 1, the theta, the definition, is that computable from phi, from the definition of the?
Yes.
Okay. Mm-hmm.
Yeah. A good question. Okay. So right. Okay. So let me tell you what the extension is. So suppose we're presented with a class. Okay, so I have a first order definition phi, that's in the language of set theory, and I've got a parameter z, that's a set, and I'm defining the class of all x. So maybe it's the class of all ordinals, or the class of all, or sets that are in L of z, or something like that. Okay, some class of objects, then, so I have phi and the parameter in hand. Okay, and now Okay, in general, of course, we can't use the class itself as the extension because that's might be a proper class. But I want a set, it has to be an object, right? So it's no good to take this class as the extension. So instead, I'm going to use the data of the presentation itself to define what the extension is. Okay, and this is how I'm going to do it. Given the class, I consult a fixed enumeration of formulas. Okay, and phi appears in that list. But maybe there's some earlier formula and some parameter that is equivalent to phi. Okay, so I take the earliest formula that could define the same class. Okay, and then with that formula psi, I look at all the parameters of minimal rank that work. So it's like Scott's trick. I'm taking the earliest possible formula that could define the same class and the set of minimal rank parameters that with that formula define the same class. Okay, and that pair is the extension. Okay, so the extension is the smallest formula and a set of parameters, the minimal rank parameters that define the same class. And that's obviously going to be a conceptual invariant, because if I have two definitions defining the same class, then the earliest formula that works and the minimal set of parameters that work with that formula to define that class is going to be the same for both of them. Okay, so in short, the extension of a concept is the smallest formula capable of defining it with some parameter together with the set of minimal rank parameters that do so. Okay, and that's a set because it's a pair consisting of a formula and a set of parameters. Okay, so now let's establish the definability claims that I made about it. Now, given a class presented intentionally, which means that we have the formula and the parameter z in hand, then there's only finitely many preceding formulas. It's a standard formula because we were given it. And so there's only finitely many preceding formulas. And so I can just make a disjunction over those formulas to find out which one is the smallest one. And so to express y is the extension, I'm just saying y is a pair of one of those finitely many such that u is the set of minimal rank parameters so that it's successful. Okay, and this assertion here is the theta that Gunther just asked about, and it's computable from phi because I'm just have to look at the ones that are previous on the list, and it's this computable list of the assertions, and therefore I've got this disjunction saying, you know, identifying the earliest psi that works. Oh, here I'm calling it phi sub I, right? Okay, so the key point is that because phi is given and is standard finite, this disjunction is a finite disjunction of assertions, and therefore it's first order expressible. Okay, go ahead.
I mean, does it follow that in your universe you have a total well-ordering of the whole thing?
I don't think that follows, because this is going to work in any ZFC model. Maybe V is not equal to 100.
But somehow, I don't know, perhaps I didn't get the whole.
If I had a global well order, then I wouldn't need to do the Scott's trick because I could just take the definably least parameter that worked. It would be simpler if I had that, but I don't. That's why I've got to do the Scott's trick of the set of minimal rank parameters.
I see.
I can't identify a particular parameter, but if I had V equal hot, if I had a global definable well order, then I could pick the least parameter that worked, and it would be a little simpler.
Okay.
So, okay, so that's the, right. So now we know what the extensions are, and we have the first part of the definability requirement. Notice that we don't need any truth predicate here. I'm not appealing to a truth predicate because I'm just taking this disjunction over the prior formulas on the list. Okay, so now if I have this class function, it's basically the same idea. If you give me a single definition of a class number of classes, a uniform definition, yeah, then I can do the same thing because here I is just amounting to another parameter. I can put it together with Z and do the same trick, right? So the F sub I is a class that's defined from parameter I and Z. And so I'm going to be picking out the least psi before this v and so on that defines that class, where I think of I and z as a single parameter. Okay. And so therefore I can define this class function. So if I have a class of classes, then I can get uniformly, I can define the extension objects of those classes is the point. Okay. So whenever we have a concept for a function from objects to concepts, then we have a concept for the extensions of those concepts uniformly. Okay, and now in the most general case, I have a class F, but I don't know the definition, right? I don't know which formula it is that it's defined by, but there is some formula that defines it. And the point is that if I'm in the ZF model equipped with only the definable classes, then, well, I know that for standard finite n, the sigma n truth predicates are classes, they're expressible. And those are the only, since I've only got the definable classes, I know that every single class that there is defined by some sigma n formula for some n, for some standard n. And therefore, with a second order formula, I can identify which formula it is that defines that class, because I can just ask. To say that y is the extension of f is to say that y is a pair, a formula, and a parameter set, where psi is a sigma n formula for some n, such that for every class T that is a sigma n truth predicate, and there is one, because I have only definable classes here, and so the formulas I'm talking about, I mean, the least one is going to be a standard one, and it's going to have a truth predicate, and therefore I can recognize that formula. Okay, that's a second order quantifier because I have to say for every class T that is a sigma n truth predicate. That's a first order property about T, because you're just asserting the Tarski recursion holds of T up to sigma n. And but to get T is a second order quantifier. So this is a second order definition in general of the extension object of a class F, even if I wasn't given the formula defining F explicitly, as long as I know that there is one. Okay, so that's the third definability claim in the first part of the theorem. Okay, the point is that because F is actually definable, the n that you get is going to be standard. And so there will be a truth predicate for that. Okay. I guess I should say minimal n here. Maybe it should say minimum. Okay. All right, so finally, we just observe that basic law 5 is fulfilled for this because the extension of the concept was this pair, the formula and the parameter set that defines that class. And so if I have two different classes and they're equivalent, then the smallest formula that could define them will be the same for both of them because they're the same class. And so I get basic law 5 for this definition. Okay, so that basically proves the theorem. But I want to talk about sort of aspects of this proof. Okay, so there's some prior art. Terence Parsons showed the consistency of the first order fragment of Frege's system, right? I mean, Frege's system, the basic law 5 is one of the axioms in his system, and he has, the realm of objects and the concepts on it, and he has this assignment of the concepts to objects in such a way that fulfills basic law 5. But if we take only this sort of first order definable concepts, which is basically what I'm doing here in set theory by considering only the definable classes, then in a very general way, Parsons showed that that you can do it. And the way he did it was, well, if we have, say, a countable language, then there's only countably many definable classes on a countable domain. And so I can divide that countable domain into stripes. And in the first stripe, I can use those as the extension objects for the definable classes by the formulas in the base language. And then in the next stripe, I can consider the definitions that make use of the previous extension object, so the depth 1 use of extension operator. and then depth 2, depth 3, and so on. So in omega many steps, I can assign the extension objects to the classes, even in the language with the extension operator there. Okay, so that's what he did. And Bell strengthened that in a way that's reminiscent of the Hamkins idea. Namely, he just adds these constants C sub A. So for each formula A, we have a constant in such a way that the constants are equal if and only if the concepts are equivalent, or the definitions are equivalent. And this is the kind of compactness argument that he's using here. It's simpler to think about. Right, and John Burgess also carries this out more explicitly. Okay. So then he also mounts this cardinality argument. So he wants to go from the full second order case to an elementary substructure using the Hamkins semantics for classes, and do it there with only countably many classes again. Okay, good. So I want to specifically talk about an issue of all of these arguments, though, which is that the extension assignment is not definable in any of these cases. It's not definable in, no, did I say that right? It's in none of these cases is it definable. They just didn't worry about the definability aspect, whereas I think of that as actually extremely important, particularly for Frege's use. So they specify the value of the extension object. So we've got this class F, and we're attaching to it an object, an individual in the domain that's going to represent that class in such a way that basic law 5 is fulfilled. But they're doing it from outside the model, like as though by the hand of God, it's assigning the, which object is it that is representing this concept? Well, I attach this, and then I attach over here, and so on. And there's no definability at all achieved by that process. Okay, so we can't tell. It might have been Julius Caesar attached to a certain concept, and we would have no way of expressing that or knowing that. Okay. So my account, in contrast, is deflationist precisely because I've defined the extension objects from the concepts, and I proved basic law 5. I'm not just assigning it from outside the model. And so, okay. So therefore, the use of my use of the extension operator is eliminable. Every assertion in the I can expand the language of set theory by adding this var epsilon operator. So I can talk about the extension of phi. And even if there's parameters in there, that's fine. That's exactly the uniform case, right? If I had parameters in phi, because that's also uniformly expressible. So any assertion that you can make in the expanded language that allows the extension operator is equivalent to an assertion in the base language of set theory. That's exactly what the definability part of my theorem gives us. Okay, and I find it frankly strange to neglect that identity and definability criteria. I think it should be part of the conversation of basic law 5 and extension operators to discuss definability of the extension assignment. Okay, so how is it that the extension objects get assigned to the concepts? In the prior results, it was a kind of mystery and arbitrary coming from outside. How do we recognize whether a given object is the extension of a particular concept? So this is basically the Julius Caesar problem for these concepts. How do we recognize that something is the extension of a particular concept? Or how do we recognize whether a given object is the extension of some concept? Okay, so these questions are all related to the definability of the extension assignment.
Can I just ask a question? Okay.
Sure, yeah.
So for your approach, it's of course like key that you're focusing on definable classes, right? Because
Yes,
that's
absolutely.
basically where the names come from. I mean, in a way, you're looking at them as they come with names for themselves, and essentially, right?
Right.
In a
Well,
way.
not necessarily, because I mean, in the general case, right, even when F was just a class and we didn't know which definition, then it's still definable in the second order case, but only in the Hamkins model, which has the definable classes.
Yeah,
so you're totally right about that. Okay, and of course, it's impossible to do it in the full second order logic because Russell refutes that case, right? I mean, it's contradictory to do more than that. Okay, the point is that the contradiction is up there, and it's not at the level of what I'm talking about here, which I also argued is the actual case. That's what we do. That's what the quotes by Bloss and Kanamori were attempting to show, that if we do first order ZFC set theory, then those are the only concepts that we have, in fact, the definable.
Even though you don't agree with Kanamori on
I
that
don't, yeah,
one
I
point.
don't
Yes. Okay.
Okay. So, right, exactly. Okay, so right, so this is why I say that my account is deflationary, because I can eliminate the epsilon. It's expressible in the language without, yeah, in the semantics for extensions that I provided. Every use of that operator is eliminable. Every assertion in the language allowing it is equivalent to an assertion in the language of set theory in a computable way, even. Okay. Yeah, primitive recursive even. Okay. So, right. Okay, so how do we reconcile this with Russell? Because I mean, you often hear people say Russell refuted basic law 5, and people say basic law 5 is inconsistent. And I'm exactly disputing that way of describing the situation, because here I've proved basic law 5 as a theorem scheme of ZFC. And so how could it be inconsistent? And the point is that the inconsistency is not really in basic law 5 itself, but rather it's coming from some other implicit assumptions that are built into Frege's system in his manner of forming terms. Okay. The most natural formulation of Russell's argument is a refutation of general comprehension, and this is usually how it's presented, at least in a set theory context. We show that it's refuting the general comprehension principle, right? The idea that you can, for any property, you can make the set of all instances of that property. That's the false comprehension principle that Russell refutes, even with this trivial case, right? The collection of all X such that X is not an element of X cannot be a set, because then it would be an element of itself if and only if it's not an element of itself, which is a contradiction, and therefore that's the Russell refutation of this principle, right? Okay, but the historical problem is that general comprehension wasn't explicitly part of Frege's system. And so both Frege and Russell describe what they had done as refuting basic law 5. The general comprehension is sort of hidden away into the, basically it's built into the notation of forming terms. Okay, so Frege blamed basic law 5, but he hints at this systematic problem. So he says, my explanations do not suffice to secure a meaning for my combinations of signs in all cases. And so that's what I meant by it's sort of built into the notation. Okay, so let me first explain, how is it that Russell's argument refutes basic law 5 instead of general comprehension? So let's just go through that. Basic law 5 is inconsistent with the existence of a concept that asserts X does not fall under any concept of which Y is the extension, of which X is the extension. Okay, so this is sort of like being non-self-membered, right? X isn't a member of the concept of which it is the extension. Okay, if we have that concept, then we can refute basic law 5. So if R is the concept, X does not fall under concept of which X is the extension, then let little r be the extension of it, which is now an object. And by basic law 5, any concept of which R is the extension will agree with this concept because it's the extension of that concept. And so therefore little r falls under R if and only if it doesn't, and that's the Russell contradiction. Okay. So we're refuting basic law 5 together with the existence of this certain concept. Okay. And that's the main point I'm trying to make. We're not just refuting basic law 5 itself, we're refuting basic law 5 together with this concept existence assertion, which is something like an instance of general comprehension. Okay. So if we had the falling under concept, this is sort of Frege's way of talking about. So X falls under, in other words, X satisfies the predicate of which Y is the extension. X falls under the concept of which Y is the extension. If we had that concept, we could express this one. Okay, so therefore so Russell has refuted basic law 5 together with the existence of the falling under concept. Okay, and And now the point is that, the point I want to make is that the falling under concept is basically a truth predicate. It's a satisfaction class. We can think of it like a satisfaction class or a truth predicate, because the extension of a concept is like, you know, the object that's describing what that concept is. It's like the formula, basically. And so to say X falls under the concept of which Y is the extension is like saying X satisfies the formula phi, but as a uniform thing. So the falling under, I'm trying to emphasize the point that the problematic part of Frege's system wasn't basic law 5, but rather that he built in a truth predicate by having the falling under concept available. Okay. So this falling under is pervasive in Frege. For example, for Frege, a natural number is an object that has every property of 0 that passes from a number to its successor. So how do you say that? Well, you need the falling under, right? So to say, right, a natural number is an object that has every property of 0 that necessarily passes from every object to its successor. So inductively, it would get up to that number, right? Or the property of being a natural number itself would exclude everything else. And so he's using this falling under concept at the core of what he's trying to do, this logicist project that Heim mentioned, right? This falling under is pervasive in Frege. He's really using it everywhere. Okay, now what I want to do is show how to prove Tarski's theorem directly from Russell's argument. Now, okay, so Tarski's theorem says that we can't express truth. So let me formulate it like this as a binary thing. There's no formula Tyx, so that for every formula phi, T of phi x if and only if phi x. Okay, so this is saying phi is true at x. Okay, there's no formula that fulfills this property. It's a way of saying satisfaction is not expressible in the language of set theory. So let's prove it directly from Russell instead of from Gödel. Okay, I mean, the sort of traditional way to do Tarski's theorem right is first you prove Gödel's theorem, and then a kind of afterthought, you prove Tarski's theorem by taking a fixed point and so on. But I'm going to prove it directly without any fixed point. I'm just going to go directly from Russell and prove Tarski. So let R of X be the property that it's saying X is not true of X. Okay. So, and then I need to have, I mean, I've put these Gödel brackets on here, but really very little is needed in here. I just need to know that every formula is represented by an object. Every formula is represented by an object. This is going to be a formula. I mean, we assume that we had a formula. So R of X is a formula. So this is the object that represents it. You don't need to put the whole syntax and so on. You can completely avoid all the Gödel arithmetization of encoding the syntax. None of that is needed for this argument. All you need is to know that the formula itself is an object, which in set theory is sort of how we think about it anyways, because a formula is coming from the parse tree and so on. And this is represented in set theory like any finite combinatorial object, if we think of set theory as a foundation. Okay, so R is the formula big R, and we look at R of R, and it asserts not T of R, which is, of course, asserting this, which by assumption is equivalent to not R of R, contradiction. So it's exactly the Russell reasoning here, but it's proving Tarski's theorem, which didn't come until decades later, right? And so there's an argument like this in fitting. He has a nice argument, although he doesn't do it like I do. So his version of it is more complicated than this because he does the sentential form. I'm doing the satisfaction class instead of the theory. I have it a binary truth predicate instead of just asserting that a sentence is true, which is how he does it. And then he needs to code the whole syntax in and do the whole Gödel arithmetization stuff and find the fixed point. But I don't need any of that. If you separate it out, then you don't need to encode in the syntax. Okay, but it's a very nice paper that he has. One can think about it like this: if truth were expressible, then we would have a formula that asserted phi is not true of itself. and then it's just the Russell argument to get the contradiction from that. So that's a proof of Tarski's theorem. Okay. This is my new favorite way to prove the incompleteness theorem, is like this, because you first prove Tarski's theorem, so you know now that truth is not expressible, but provability is expressible because of arithmetization. So therefore, they're not the same. And that's the content of Gödel's theorem, that truth and provability are not the same. Okay. So, right. Okay, okay, this is just summarizing things I've already said, so I'm sorry, it's a little redundant. Okay. Okay, Tarski's theorem implies Gödel's, as I just mentioned. So this is my favorite way to prove Gödel's theorem now, is via Tarski. Okay. So this, to my way of thinking, also shows how close Russell was to Gödel's theorem, because it was so soft and easy to get Tarski's theorem from Russell without Gödel. And so Russell basically almost had Gödel's theorem. I mean, one can see it this way. Okay, you still need to do arithmetization, which is what Russell was missing. So in order to really know that truth and provability are not the same, you need to formalize provability in arithmetic. And so that's what he's missing. So Gödel's, maybe one of Gödel's most important achievements, of course, was arithmetization. Okay, so let's go on. Truth is not a concept. This sort of the falling under relation is not a concept. That's, you know, we can easily, for a given concept, we can express x falls under phi. Okay, that's just saying phi of x. That's what phi of x says. X falls under phi of x. So what we're refuting is this sort of uniform account of x falls under phi. You know, and that's very much like Tarski's theorem, saying there's no uniform way of expressing truth. We can express truth of an object for a given particular formula phi, no problem. Phi of x, that's what it says. It says x satisfies phi. But what we lack is the uniform account. So the problem with Frege's system was that he built in this truth predicate, basically, because he could express in a simple line, because of notation, x falls under the concept of which y is the extension. Okay. Okay, so let me give some further applications. So let's see, what time is it here? Okay. So, right. There's other Fregean abstraction principles. I mean, the most famous, of course, is the equinumerosity relation. So two classes are equinumerous if there's a one-to-one correspondence between them. Maybe they're sets, maybe they're classes. Okay. And the number assignment problem is the problem of assigning an object to each class in such a way that it's an equinumerosity invariant, which is to say the number of x's is equal to the number of y's if and only if they're equinumerous, right? This is the cardinal assignment problem, or the number assignment problem. It's often called Hume's principle, but I like to call it Cantor-Hume principle because Cantor, of course, used it so impressively. Okay, so the theorem is that in ZFC there is a number assignment scheme fulfilling the Cantor-Hume principle. Okay, I'm going to do it in exactly the same way that we did it for the extension objects. In certain cases, there's much easier solutions, right? Okay, if I only want to assign numbers to sets, then of course the standard solution in ZFC is to just take the smallest ordinal that's bijective, right? If every set is well ordered by the axiom of choice, and I can assign to every set the smallest well order that's equinumerous with it, and that's the cardinality of the set, that's the definition of the cardinality, and that is a number assignment, a solution to the number assignment problem in ZFC for sets. Okay, and it goes beyond Cantor-Hume because it's not just a solution of the number assignment problem, but it's a solution of the cardinal selection problem. We're not just assigning an invariant for that equivalence relation, but we're picking a representative from each equinumerosity equivalence class, right? Because the cardinality of a set in the ZFC definition is not only an invariant in that equinumerous sets get the same cardinality, but the cardinality itself is one of the sets that's equinumerous with the set. Okay, that's more than Cantor-Hume expresses. Okay, but in fact, you don't need the axiom of choice to solve the number assignment problem for sets. Because you can just use Scott's trick, Namely, for any set, just define the number of X to be the set of minimal rank sets of that equinumerosity class. Right? There's lots. This is the origin of Scott's trick, actually, this observation here. I had an email exchange with Scott, and when I was writing this part, and it was about something else, but I mentioned to him, I said, oh yeah, I'm mentioning your trick in this work on Frege that I'm doing, and he wrote back to me this very long message, saying, well, first of all, he explained how it was that he came up with this Scott trick. He was an undergraduate student in Berkeley in a class taught by Tarski, and Tarski had posed to the class this question, can we find invariance for any expressible equivalence relation like that? And Scott made this solution of the minimal rank instances in a given equivalence class. And Tarski really liked it a lot. And I think it's Tarski that named it Scott's trick and promoted it. But Scott said, look, I've really done so many other great things, that I'm much more proud of. And he gave me this long list of accomplishments. And of course, I mean, I don't need to tell all of you all of his great accomplishments because he's quite amazing logician and mathematician. And so all of those things definitely were great. But he really doesn't want to be remembered for Scott's trick. Although I kind of disagree with him because I think of Scott's trick actually as a very fundamental observation that comes up again and again and again. It's important in ultrapowers. It's important in forcing. If you take the Boolean ultrapower approach to it, it just comes up again and again and again. And here we're seeing it here in solving basic law 5. And so it's a really fundamental observation. And so I disagree with Scott that he shouldn't be remembered for Scott's trick because it's really key to a lot of things. Okay, so we can solve the number assignment problem in ZF without the axiom of choice if we just define the number of a set to be the set of minimal rank sets in its equinumerosity class. Now that won't solve the cardinal selection problem because the collection of minimal rank sets is itself not equinumerous. It's a bunch of sets that are equinumerous, but it's not itself equinumerous. Okay, but it fulfills the Cantor-Hume principle, which is only about the invariance property. Okay, but really Cantor-Hume is about classes and not about just sets. So we want to solve it for classes. We want to assign numbers to all classes, not just to the sets. And if we have global choice, for example, like Chaim was asking about earlier, then then we have a definable global well-ordering of the universe, and there's only one more equinumerosity class because all proper classes would be equinumerous with each other in this case. And so we would only need one more number. And so we could do it. So with global choice, we can assign the number of a class F is the smallest ordinal global choice implies the axiom of choice. So we can, the cardinality of a class F is the smallest ordinal equinumerous with it if it's a set, or there's some default value, which I can call infinity when F is a proper class, and that is going to be a solution of the cardinal selection problem. Okay. And therefore also the cardinal assignment problem. Okay, so, but if global choice fails, then we can have lots of different classes, proper classes that are not equinumerous with each other. And so let me explain how one can solve them without any choice principle in the case where we have only definable classes. Okay. So we have a lot of different proper classes, and they might not be equinumerous, but we need to assign them each a number. And we can do so using the same method as I used in the basic law 5 argument. Okay. If we have definable classes, I'm going to assign a number to it so that if it's given intentionally, then I can identify the number with a second order property, and they satisfy the Cantor-Hume principle here, so that the number of F's is equal to the number of G's if and only if F and G are equinumerous. Okay. It's not surprising that we get a second order expressibility here and not first order, because the equinumerosity relation itself is second order. To say that two proper classes are equinumerous is a second order property, because you're saying there is a class which is a bijection between those classes, and that's a second order quantifier. Okay, so that's why this, in the basic law 5 case, we had first order expressibility here, but now I only have second order. But it's not surprising because the equivalence relation I'm talking about is second order, whereas for basic law 5, the equivalence relation was for all individuals x, fx, if and only if gx was a first order expressible property. Okay, so, right, so what is the number assignment? Well, the number is just the pair consisting of the smallest formula and the minimal rank parameters that define a class that's equinumerous with it. So I'm using the smallest instance, the smallest definable instance that could define a class that's equinumerous with the given class. Okay. And in order to express that it does so is a second order property. Okay. But because this definition depends only on the equinumerosity class of F, it's going to fulfill the counter-Hume principle. It's going to be an equinumerosity invariant. Okay, right. This is the point that I made already, that equinumerosity itself is second order. Okay, so let's go. Of course, Frege abstraction is really about any equivalence relation. The idea is that if you have some equivalence relation you want to attach to each equivalence class in object, right? He has the example of parallelism, the direction of a line. So two lines have the same direction if and only if they're parallel. But what is the direction of a line? What is it? Well, for Frege, it's an invariant for that equivalence relation. It's something such that two lines have the same direction if and only if they're parallel. So that's a solution of the Frege abstraction, which I can express like this. For any equivalence relation at all, the abstraction is an assignment of objects to their abstractions so that we have identity of the abstractions if and only if the objects are equivalent. So, for example, if this is line X is parallel to line Y, if and only if the directions are equal. Or, you know, whatever other equivalence relation you have for the number of, or the, you know, same shape, or whatever equivalence relation you're talking about, then Frege abstraction is an assignment of the abstraction. Now, of course, we can take equivalence class, and that would be a solution of the Frege abstraction. So if we're only looking at equivalence relations on sets, for example, then we can also combine it with Scott's trick. The equivalence class might be a proper class, but with Scott's trick, we can just let alpha x be the set of minimal rank members of that equivalence class, and that's going to be a solution of Frege abstraction. But that's only for objects x, y. We really want also the case when the equivalence relation is on classes, which it was for Frege. So equivalence relations on classes. So now I, for example, this is the kind of thing that comes up in basic law 5, right? We want to say one class is equivalent to another class if they have all the same instances. Right, exactly. This is basic law 5. I mean, this is the equivalence relation that's underlying basic law 5. And the basic law 5 is saying that we have a solution for Frege abstraction for this equivalence relation. That's what basic law 5 is saying. Okay, but in the general case, we have some equivalence relation double squiggle, and we want a solution of this. So an object alpha f that represents the double squiggle equivalence class of f. Okay, but we can do it just like the other methods. So if it's a first order definable equivalence relation on definable classes, for example, the one that's in basic law 5 is like that, then we can assign the abstractions, and for any particular expressible one, the identity relation for the abstraction is going to be expressible in first order logic. Okay, and right, and the method is just the same as what we used before. For each definable class, we take the first formula that can define it with some parameter and the set of minimal rank parameters that do so, and we let the abstraction be that pair. And the argument is basically identical to what we did before, and that's depending only on the equivalence class of f, and so therefore it's invariant. Okay, and then so this.
I cannot.
Go ahead.
I'm sorry. I don't want to interrupt, but in the case of parallelism, which is a standard example,
right,
obvious that by doing this, you get a system which is a conservative extension of the previous system.
So
if you add, for instance, directions as
Right.
new objects, then you can reduce every case to a case in the language without this, and you show that this is a conservative extension of the previous system. You don't get any new things. And I think this is also a general property of what you are doing.
No, and I disagree. And first of all, I'm getting that also. That's exactly my eliminable claim, right? That's a conservativity claim.
Yes.
Okay, but the difference is that in the case of parallelism, like if we're doing set theory, then the lines are first order objects. And so I can just take the equivalence class. I already have a definable abstraction, say in set theory for parallel lines. I can just take the equivalence class. That's the easy case. The hard case is when the objects themselves that the equivalence is getting applied to are themselves concepts, right? When they're already classes, that's the hard case. And that's what this argument on the screen now is about, right? So here, F and G are not going to be lines because lines are objects, not classes, right? So the parallelism of lines is easy to get extensions for, abstractions for, because I can just take the equivalence class. And that's the sort of standard mathematical move. We're taking quotients all over the place, which is in effect doing Frege abstraction. Whenever you take a quotient of a mathematical structure, you're doing Frege abstraction because the equivalence class of an object, in a realm is a Frege abstraction for that object. It's a solution of the abstraction equation. But in the most general case, and the one that's underlying basic law 5, it doesn't work because the objects themselves are proper class size things, like the concept F and the concept G. We want to assign an abstraction to having the same course of values. So it's a much more delicate problem. And so I think in order to know that you can do it in such a way that it's conservative, as you said, the only way I know how to do it, say in the ZFC context, is with my argument here. I think this is the new contribution I'm making.
So what is a kind of a new theorem that you have that you cannot do it without?
Well, when I had the slide on the prior art, right? They had so Parsons and so on, and Bell and Burgess. They didn't have the definability aspect of the assignment, right? And so that's what's missing from the previous conservativity results, even, right? The definability of the extension operators.
But from a general point of view, when you use your system, do you get actually new results in set theory?
Oh, I see. Well, that's asking too much, isn't it? But if it's conservative, then we don't want to be able to do that, right? Or what?
But in yours, you can.
Okay, I'm not quite sure I understand the question.
You say, when you say it is, what do you call it? Deflationary.
Right.
Deflationary means that actually, the term deflationary, can mislead here, but this is another thing, because usually deflationary means truth is not an important property of a formula. This is the general notion of deflationary.
Oh, I see. But no, is that right? Because that's when you're talking about sort of deflationary accounts of truth. Yes, I agree with what you said. But to me, the word deflationary means that for some phenomenon, you have a deflationary attitude towards it if you're showing that the use of that, extra resource is.
Yeah, I understand.
Yeah.
But just the classical deflationary means, in general, this is claiming the philosophy of language that truth is not an important, interesting thing to say that certain sentence is true, because it's a way of really, cutting short something which is not an essential addition. That's a general notion of deflationary.
So when I was using the word deflationary, I just was meant to refer to this conservativity elimination result. Yeah, that's all I meant.
But you take this with your account, and it doesn't, is there any new, I mean, is there any new theorem in ZF that you can prove if you assume what you assume?
I'm not sure. I mean, what I'm claiming is that the use of the abstraction operators are illimitable. So therefore, no, right? Except I'm also proving a theorem in ZFC. You know, the fact that that's true is a new theorem, as far as I know, and so that's the new theorem. But of course, I'm proving it in ZFC. I'm not using. I'm defining the abstraction operators in the language of ZFC, right? So why don't I finish up and then we can have a general discussion.
Okay. Sorry.
Okay. So what have I done? Right, I've defined Fregean abstractions, and this is including the case of equinumerosity and equinumerosity of sets and so on. But equinumerosity of classes is a second order notion, and so we have then a more complex assignment because of equinumerosity being itself second order. Okay, so that's it. Thank you very much.
Thank you very much. Very interesting. Let me see. Okay. Okay, so we had a lot of questions already during the talk. Are there any more questions or comments?
Yeah, I have a question.
Some people have their hands up also, I noticed.
Yeah. Can you hear me? You can't hear me?
Yes, I can hear you.
Oh, okay. What you did in the first place, I mean, the basis of everything, isn't that just elimination of imaginaries in set theory?
Yeah, I think so. I think
wrong.
there's a sort of model theorist way of describing
Shalaf's imaginaries, the definable, the concepts can be seen as objects in MEQ, and then it's, you know, it's exactly. I think this is in the textbooks also.
Oh, I see. Okay,
Yeah.
So you're saying the theorem itself is following directly from Shalal or what?
No, it's not. Well, I'll dig it up. I mean,
okay, yeah. If you could send me,
I just know
there's
that
actually the paper. I still have a chance to edit. It was just accepted, and so if I can put in that reference, it would be great. Yeah.
Yeah. Okay.
But I think you're right. I mean, it's a way of understanding. Of course, the argument isn't very difficult, and Scott's trick is, of course, well known. But right, I think that, you know, it's this connection with basic law 5 in particular that I find particularly interesting.
Yeah. No, I'm the rest of it is very. I'm just saying that elimination part that you can actually, that you have epsilon f in the theory,
Right,
as an object.
Okay, yeah, I want to look into that more. Thank you.
Could I make a tangentially related comment?
Sure.
Because some years ago I was trying unsuccessfully to defend Frege, and let me summarize quickly what I had in mind. If you look at Freges system and think of domain of objects, and then there are these concepts which I thought of as, you know, subsets of the objects, power set,
Right,
power class, whatever. And basic law 5 says there's a one-to-one map of the power class into that class. And the first point was, surely Frege knew Cantor's theorem that you can't map the power set of X one-to-one into X.
right.
In fact, I think it's in the same book that he actually gives Cantor's theorem and the proof thereof. You know, so what could he have been thinking when he wrote down basic law 5? And my attempt to defend him was, he may have been thinking of concept not the way I do as class, but as definable class, in which case there may be far fewer of these concepts, and maybe there's a perfectly good one-to-one map.
I see. It's really fantastic. I really like it.
And yeah, so what if you were thinking of definable classes? Of course, basic law 5 is still inconsistent, but it's not the sort of thing that he obviously should have known is wrong.
Right.
In view of Cantor's theorem. it turns out to be wrong anyway, but for a more subtle reason. Namely, if you think of concepts as definable classes, now he's introducing this Wertverlauf, or extension operator, down to the objects.
Right.
And he's using that to define some classes, like the Russell class, for example.
Right.
He's used definability to introduce this Wertverlauf operator, and then use the Wertverlauf operator to create new concepts. And it's that loop that turns out to be the real danger.
Exactly. That is exactly what I was trying to say with the falling under. It's this,
Yeah,
this second part of the loop is exactly the falling under relation. And that's basic law 5 itself for definable classes is not inconsistent.
Definable classes is fine, but the loop is not.
Exactly.
And this was my attempt to defend Frege by saying he was thinking of definability and not thinking carefully of the fact that he was introducing a loop there. So what I mentioned this a couple of times in some talks, but then decided to check with a Frege expert, Jamie Tappenden. Since we just happened to have a Frege expert a few buildings away from our department in Michigan. And he was not at all convinced by this.
I see.
Basically because he found places in Frege's writings where Frege essentially allows creation of additional concepts. Concepts are things you can say in whatever language you're using, and he allows for extensions of the language. And by doing that, he basically shoots down my attempted defense.
I see. Okay.
Frege, if you extend the language to include the Wertverlauf operator, you're right back in trouble with Russell again.
Right.
So this never
Quite
went anywhere, but it was a nice idea while it lasted.
right. If you
Just
have
to-
any
just to this
resources, let me just, I want to just say something to Andres. If you have any resources about that, what you just described, like your talks and so on, I would definitely be interested in
I
that.
might still have some slides
Yeah.
from talk
Because
that
it
I
sounds like what you were talking about was very similar to the line that I'm taking here.
Yeah, I'll have to see. It was quite a while ago, and
Right.
it may have. It was certainly not on this computer, but there are other computers where it might still be findable.
Just to this point, Frege himself says that he was always suspicious of this axiom.
Yeah.
And if so he felt that there was something wrong with it. And he said in the Grundlagen, he says, well, you know, philosophers spoke of extensions, so let us take this and let us define it by extension. But he was always not very satisfied, and he was anxious about it.
Yes. And of course, more anxious after Russell came along. Maybe another tangential point. If you look at Basic Law 5, it says the extensions are equal. Sorry, yeah, the Wertverläufe are equal,
Yes.
if and only if the concepts have the same, apply to the same elements.
Right.
This looks to us nowadays like an axiom of extensionality.
Right.
They have the same members, they're equal. But the part that leads to the contradiction is the converse. And if you think of the extension as being the class, the converse looks silly. If the class of F's equals the class of G's, then of course F applies to the same things as G. But it's that direction that says that Wertverlauf is a one-to-one map, not just a map, but a one-to-one map from concepts to objects. And that's where the contradiction came from. So the usual way of thinking of Frege's system in light of modern tendencies is basically messing up both what he got right and what he got wrong.
Very good.
Joel, can I ask, with the falling under principle, what was the relationship between X and Y?
So if you have a truth predicate, right, you can think of it as saying X is an object that satisfies the formula phi, right? I mean, a satisfaction relation or truth predicate would be stated in such a kind of way. And so the falling under is just like that. X is falling under the concept of which Y is the extension. So Y is like the Gödel code of a formula or something like that, or it's the extension of a concept. Yeah, it's the thing that's representing the concept in the same way that a formula represents the class it defines. And so the falling under relation is relating X to Y if X is satisfying or fulfilling the concept that is represented by Y. So I view that as like a kind of truth predicate. And that's the sort of, in my view, the origin of all the trouble is that he can express, there's a formula that expresses in Frege's system the falling under relation. That's the real problem with his system. And it's not basic law 5 very much. Of course, you use basic law 5, you know, in order to carry out the argument, but the real source of the difficulty is that he's got a truth predicate built in.
So it's not like there's X and Y are like referring to each other. It's just that the concept itself is.
Y is representing the concept and X is fulfilling it. That's what the falling under relation is.
Okay.
X, I mean, this falling under is Frege's way of talking about it. X falls under a concept means that it fulfills it or satisfies it. 5 falls under the concept of prime.
But like the concept itself is somehow like a formula or something.
Yeah, it's this predicate on the domain of all objects.
Okay. Any more questions or comments? These were great questions and comments, by the way. Any more of this? Okay.
No,
I think
Marcus
we're-
is holding his hand.
Oh, I couldn't see. Sorry. Please just
Sorry.
speak up if you have a question.
Yes, if I may. This is fascinating. Thank you very much. I have two. Well, I've got one question, but one follow-up to the discussion we had before, if I may. When you say that falling under is expressible in Frege's system, what exactly do you have in mind?
Yeah, so X falls under Y. Oh, well, go ahead if you have more.
No, please.
Yeah. I think you can say, let's see, X falls under Y. X falls under Y, under the concept of which Y is the extension, is just asserting for every capital F, if Y equal var epsilon F, then Fx. So it's just expressible. It looks like a second order quantifier because it's for every capital F, but we have the var epsilon built in, and this is exactly the sort of closing of the loop that Andreas had mentioned in the loop he was talking about, is exactly the fact that we can use the epsilon operator to express that Y falls under the concept of which Y is the extension.
So that relation is defined in Frege, right?
Yeah.
In a system. If that is defined, it must come from somewhere from which he defines it.
He's using it all over because he uses it to define what a number is, what a natural number is.
Right. Yeah. But it's a falling under. I was wondering whether that's the relation you meant. And but that is a defined notion. Right. So the only primitives are the truth functions, the quantifiers, the definite description operator, and the extension operator or the value range operator.
Right, exactly. Yeah. That's what I mean when I said it was built in. It's a matter of notation that concept exists for him. It's just built into his notation.
Right. Okay, good.
Yeah.
Yeah, thanks. Okay, cool. The question was, sorry, Professor Gaffner said the follow-up, and I'll let you go first,
Sure.
obviously.
Okay, I mean, when you try to derive a contradiction in Frege's system, when I taught this, then the obvious thing was to use it, there exists something such that this falls under it, and so you do it, and then you get the contradiction. It's far less obvious than getting the Russellian contradiction straight away. So for students to see how the Russellian contradiction can be translated into Frege's system, the standard way that I used is to use is an F and taking F of X as given. That means you can use F of X where F is a variable.
Yeah, I think that's exactly right.
the point that you have been making.
Yeah. So I mean, I tried to give in the slides. I had a slide where I tried to give the way to use Russell's argument to refute basic law 5 instead of using it to refute general comprehension. Refuting general comprehension is a kind of triviality. It's a one-line proof, but refuting basic law 5 is much more subtle for the reasons that Haim just mentioned. But it follows similar things, but you end up using this falling under idea, right? Okay, Marcus, you had more though, right? Or
just a question about well, this may be a bit silly, but the version of basic law 5 you consider is a special case of Frege's actual formulation. Right? So for Frege, basic law 5 is about functions, and concepts are special cases of functions. That's why the epsilon really is what we represent as epsilon really is the value range of a function. Does that does what you're doing work if you consider the general case of a function?
oh, I see. So right, so basic Frege has this sort of course of values, and the concepts, I mean, are just the course of values where all the answers are either the true or the false. But of course, he's looking at arbitrary functions. That's what you're referring to, I guess. And so, right, I haven't thought about that, but I think, let's see, in the set theoretic case, so again, I'm doing set theory from a Fregean light instead of Frege from a set theory light, right? And so then I think the difference sort of evaporates because a class function can be viewed as a 0-1 course of values for the pairs. And so I think it's just going to reduce. So I would expect it's just going to fall immediately out, because to have a class function is the same thing as to have a predicate on the pairs. Yeah, the input-output pairs. And so I think it, so I think I'm going to get it straight away from the other one, is what I would expect.
Thanks.
But,
Sorry, just to the point. I mean, this is the big advance that Frege considers when he goes from the Grundlagen to the Grundgesetze. Because for him, he doesn't want the trick of doing pairs and so on. This is not Frege, because he thought that the course of values is really the natural generalization from the case of a predicate.
right.
And this is a new concept that he sees as a big advance in the Grundgesetz.
But meanwhile, if we're doing set theory, we do have pairs. So
Yeah,
it seems entirely unproblematic to just use the pairs.
Yes, but Frege didn't conceive of himself as doing set theory.
Sure, right. I totally agree with that. Yeah.
I mean, he was, the relation between Frege and Cantor are very complicated, I think. And Frege didn't like some things that Cantor did and so on. There's place for some historical research there.
I think Andreas is talking, but he's muted.
Okay, sorry about that. I hope I'm unmuted now. I'd like to make a historical point about this. We can consider a function as a set of pairs and so on. As set theorists, somewhere very early in the first course in set theory, we learned how to represent ordered pairs as sets. But we sometimes also learn that this is the Kuratowski definition and that there were other definitions and so on. I don't think there were any such definitions at the time of Frege, Russell, paradox, and so on. I think the first reduction of ordered pairs to sets was somewhere in the neighborhood of 1910. I think it was explicitly mentioned as an advance by Russell and Whitehead in either a later edition or a later volume or something of Principia. So what Haim said about
I see.
bringing in multiplace predicates was more important in Frege's day than it is nowadays.
Right. So was it the Kuratowski pair in 1910, or was it someone else first and then Kuratowski later, or what?
I don't remember because I did not. I confess I never read Principia very carefully, not even the introduction. So I'm going by what I once read ages ago, later than 1910, but very much earlier than now. And I don't think I can give a good reference for that. Also, I need to apologize. I'm going to need to leave in just a couple minutes because I have an appointment at 11:30.
Let me just very quickly add to that, that Frege did define ordered pair in the basic law of arithmetic. Of course, he did it on top of value ranges. But
Oh, I see. Right.
he does have a definition.
Okay, thank you.
Okay, any more comments? Okay, well, maybe we should just thank Joel again for this very interesting talk. And
Thank you so much. It's a pleasure to be here.
Thanks very much, Joel. And we don't have a seminar next week, but we do have our last seminar of the semester the following week.
okay. All right. Have a nice weekend, everybody.
Okay,
Okay,
bye.
thanks,
Bye.
Joel.
Thank you very much.
Thank you, Joel.
Sure,
Bye-bye.
bye.
Thank you, Joel.